Before you spend a single dollar on atmospheric electricity devices, and I mean this seriously, you need to understand something that almost nobody on the internet is willing to tell you. The reason it's not being done at scale isn't because the government is hiding it or because big energy is suppressing it. The reason is far more practical, far more honest, and it's going to save you money and heartache if you know it going in. My name is Frank, and I've been living off-grid for 11 years. I've built everything from hand crank backup generators to small solar arrays that actually work. I've made plenty of mistakes along the way, expensive ones, and I've learned which shortcuts work and which ones will leave you standing in the dark wondering where your retirement savings went. What I'm about to walk you through isn't going to sell you a product or convince you that the sky is an infinite battery. What it's going to do is show you the actual honest truth about atmospheric power collection, what it can legitimately do, what it cannot do, and most importantly, why the math matters more than the marketing. Here's what is actually true. The atmosphere does hold an electrical charge. That's not controversial. It's not hidden. It's basic atmospheric physics, and you can read about it in any legitimate scientific text. Between the ground and the ionosphere, there exists a voltage gradient of roughly 100 to 300 volts per meter of altitude. That's measurable. That's real. But here's the part that changes everything. Measuring a voltage and extracting usable power are two entirely different things. Think about it this way. If I told you there was a 1 volt difference between the north side and the south side of your property, you'd be right to ask, okay, but how much current comes with that voltage? Because power, actual usable electrical power, is the marriage of voltage and current. You can have enormous voltage and virtually no current, and when that happens, you have potential energy sitting there with nowhere to go. It's like having a massive dam with a trickle of water behind it. The water is there, the height is there, but the flow is so thin that no turbine on Earth can harness it efficiently. Now, the reason I'm telling you this isn't to kill your enthusiasm. It's the opposite. I want you to understand what actually works, so you can build something that will actually serve your retirement years, not drain them. The atmospheric electrical systems that people talk about online, the ones they claim will power your entire home for $30 in copper wire and capacitors, they operate on a principle that's scientifically valid but practically limited. They can trickle a charge, they can maintain a battery in very specific conditions with very specific setups, and with realistic expectations, they can contribute something to your energy mix. But they're not going to power your air conditioner, they're not going to run your refrigerator, they're not going to turn on the lights in your living room. What they can do, and this is where your money actually gets protected, is far more interesting than the marketing videos suggest. They can work alongside other systems. They can provide a slow, steady trickle charge to battery banks during times when your solar isn't producing or your grid connection is unreliable. They can be part of a layered approach to energy independence, but only if you build them correctly and you understand their actual limitations going in. Here's what most people get wrong. They watch a video showing someone with a copper antenna collecting atmospheric electricity. They see a meter registering a voltage, and they assume that means power is being generated and stored at scale. What they don't see is how much current is actually flowing, how long it takes to charge even a small capacitor bank, or what the real-world application turns out to be once you factor in the components, the time investment, and the installation labor. They see the headline. They don't see the math. And when you're on a fixed income, the math is everything. Let me give you the honest breakdown. An atmospheric energy collection device, sometimes called a radiant antenna, sometimes called an atmospheric electricity harvester, requires three things to function: a conductor that extends high enough to be in the electrical field, a ground connection that's equally robust, and a capacitor bank or battery to store whatever charge you do collect. The conductor needs to be copper or another excellent conductor. The ground needs to be genuinely grounded, not just connected to your home's water pipes or electrical ground, which won't work the same way. And the capacitor system needs to be sized appropriately for whatever trickle charge you're actually collecting. The cost we're talking about for a functional setup, not a toy, not a science fair project, but an actual working system that can contribute something real to your energy independence, is between $70 and $200, depending on your location, your soil conductivity, and how much height you can achieve. Is that $30? No, but is it genuinely cheap compared to a solar panel? Yes, it absolutely is. A 30-watt solar panel costs $60 to $80. This will cost you $30 more. And here's where it gets interesting. Unlike a solar panel, which depends entirely on sunlight and therefore shuts down at night and underperforms in winter, an atmospheric energy system works in overcast conditions. It works at night, it works in winter, it doesn't care what time it is or what the weather is doing as long as there's a voltage difference in the sky. But here's the hard truth that the YouTube videos skip over. An atmospheric energy system will not charge your battery bank as fast as solar will. It won't come close. On a sunny day, a 30-watt solar panel will push maybe 2 to 3 amps into a battery bank at 12 volts. An atmospheric antenna system, in realistic conditions, might push 50 milliamps. That's 1/60th of what solar produces. So why would you build it? Because it's not about replacing solar, it's about layering. It's about having multiple sources so that when one isn't performing, another one is picking up the slack. And that matters for someone on a fixed income in ways that people who are still working don't always understand. When you have a retirement check that comes once a month and you don't have the flexibility to earn more money if an unexpected bill comes, redundancy isn't a luxury, it's survival. If your only power source is solar and you go through 4 weeks of December cloud cover, you're in trouble. If your only backup is a generator that requires gasoline and fuel prices spike, you're stretched thin. But if you have 3 or 4 different systems all contributing small amounts of power simultaneously, solar, atmospheric, maybe a small hydro setup if you have running water, and a hand crank backup, then you have resilience. You have insurance, and insurance is what lets you sleep at night when the power company keeps raising rates. Now, the reason I'm spending this much time on what atmospheric energy systems actually do and what they don't is because I want to protect you from the most expensive mistake I see people make in the off-grid world. They get excited about a new technology, they see a compelling video, they spend money on something that doesn't match their expectations, and then they get frustrated and give up on energy independence altogether, even though they were actually on the right track. The atmospheric antenna is not the magic bullet. No single technology is. But it is a legitimate tool that fits into a real energy independence strategy, and it's small enough and cheap enough that you can build it yourself, test it, measure it, and understand exactly what you're working with. And that information, that actual measurable data from your own system, is worth far more than any marketing claim. It's the foundation that lets you make smart decisions about what to build next. So let's walk through what an honest, practical atmospheric energy system actually looks like. Not the oversimplified YouTube version, not the version designed to make a video go viral. The real version that you can build this weekend that will work for decades with almost no maintenance and that will actually contribute something measurable to reducing your dependence on the grid. Because that's what we're actually here to do. We're not trying to power your entire home from the sky. We're trying to knock $50 off your electric bill every month. We're trying to have backup power when the grid goes down. We're trying to preserve some of the income you earned through decades of work so that you can actually enjoy your retirement. And that's where we're going to start. Because understanding what this is actually going to do for you is the first step to building something that will. So let's be clear about what we're actually building. This isn't a Tesla coil. It's not going to make your hair stand on end. And it's definitely not going to run your air conditioning in July. What you're looking at is an atmospheric voltage collector. Think of it like this. You already have weather happening above your house, whether you want it or not. Rain falls, wind blows, lightning strikes somewhere in your county almost every day. All of that is energy moving through the air, and most of it is completely wasted because nobody's there to catch it. What we're doing with this system is tapping into the electrical potential that's always there between the Earth and the atmosphere. On a clear day, that difference is about 100 volts per meter of altitude. Climb up 6 feet onto your roof, and you've got roughly 600 volts of static potential sitting right there waiting. Now, here's the part that matters for your wallet. You don't need a lightning strike to harvest that. You don't even need a thunderstorm. Clear skies work just fine. Winter works, night works. That's the real secret that got buried for over a century. Now, the first thing you need to understand is that we're not breaking any laws of physics here. We're not creating energy from nothing. What we're doing is very carefully extracting a tiny fraction of electrical potential that's already present. Think about static electricity. You know how you can shuffle across your carpet in winter, touch a doorknob, and get a shock? That's atmospheric voltage at work on a small scale. What we're building is just a more organized way of doing that same thing, with a system that can collect it continuously and store it instead of wasting it in one quick zap. The antenna itself, let's talk about what you're actually building. You need copper wire. 18 gauge is fine. Thicker is better, but thicker costs more. And for a first system, 18 gauge works. You're going to build a simple vertical dipole. That means 2 pieces of copper rod or wire, each about 3 feet long, arranged in a straight line at the top of your mast. The whole thing shouldn't weigh more than a couple of pounds. Your mast can be PVC pipe, it can be a wooden pole. Some people use aluminum, though aluminum has its own issues with corrosion that we'll get into in the guide that's available in the description if you want to really dive deep into the material science. The point is, simple, light, and available. Now the ground system. This is where most people get it wrong, and it's also where you get the most benefit for the least effort. You need a good ground connection. Not a casual ground, not a ground that should work, a real, low-resistance ground that sits in contact with damp earth. The best way to do this is with a ground rod. A copper ground rod, 8 feet long, driven into the earth as deep as your property allows. If you're on bedrock or hard clay, that's not practical. Then you use a ground plate, a piece of flat copper, maybe a foot square, buried as deep as you can dig, in a location that stays relatively damp year-round. Here's why this matters so much. Your antenna is only half the circuit. The electricity in the atmosphere is only one side of the equation. The ground is the other side. The voltage difference only has value if you've got a complete path from the sky, down through your system, and back into the earth. A poor ground connection means you're leaving 90% of your potential power on the table. A good ground connection means you're actually converting that potential into usable current. Once you've got the antenna and the ground, you add the collection circuit. This is where the magic actually happens, and it's simpler than you'd think. You need a rectifier, basically a one-way valve for electricity that lets current flow in one direction and blocks it from coming back. You can buy a bridge rectifier for $3 or $4. Then you add a capacitor bank to store the charge. Now, a lot of people hear capacitor and they think about complicated electronics, but what you're really building is just a modern version of Benjamin Franklin's Leyden jar. A capacitor is just something that stores electrical charge until you're ready to use it. For a small residential collector, you're looking at a capacitor bank rated for about 400 volts. This is not dangerous if you're careful. You're not pulling enough current to hurt you if you touch it, not like touching a power line, but it does have charge, so you respect it, you discharge it properly, and you don't go poking around inside it. The capacitor bank sits in a small weatherproof enclosure on your roof, or you can run it down to a basement installation if you prefer. Most people who've done this successfully run it down to the basement. Easier to maintain, easier to monitor, less exposure to weather. Now, here's where your actual power generation happens. From the capacitor bank, you run a wire down to an inverter. An inverter is a device that converts DC voltage, direct current, the kind of charge that's sitting in your capacitor, into AC voltage, the kind of electricity that your home uses. A small inverter, 500 to 1,000 watts, costs between $100 and $300 depending on where you shop. That's your largest single expense in the whole system. Everything else, the copper, the wire, the rectifier, the capacitors, the conduit, all of that might run you $30 to $50. So you're looking at a complete atmospheric collection system for somewhere between $150 and $400 depending on how big you want to go and how nice you want the components to be. Compare that to a single solar panel, which will run you $300 to $500 for just one panel, and suddenly the economics start to look pretty reasonable, especially when you realize that your atmospheric collector doesn't stop working when the sun goes down or when clouds roll in. Now, let's talk about what this actually generates. Don't expect miracles. This is real-world physics, not fantasy. On a clear day with good atmospheric conditions, a well-built collector with a proper ground system might generate 50 to 150 watts of continuous power. That doesn't sound like much, until you realize what it actually means for your wallet. 100 watts running continuously for 12 hours is 1.2 kilowatt hours. At the average American electricity rate of about 15 cents per kilowatt hour, that's 18 cents a day that you're not paying to the utility company. Multiply that across 30 days and you're looking at $5 to $6 a month. That might sound small, but here's what matters. $5 to $6 a month is $70 to $72 a year that you're generating instead of purchasing. Across a decade, that's $700 to $800 that stays in your pocket instead of going to the power company, and that's just one collector. If you've got the space and the materials, you can install multiple collectors on different parts of your property. 2 collectors gives you $12 to $15 a month. 3 collectors gives you $18 to $20 a month. Now you're talking about $200 to $300 a year, which actually starts to move the needle on a fixed income. But the real value isn't just the power generation, it's the backup capacity. Once you've installed your atmospheric collector, you add battery storage to the system. A small lithium battery bank, and prices have come down dramatically on these, can cost anywhere from $500 to $2,000 depending on capacity. But here's the thing, you can start with the collector running into a battery, and then you've got backup power sitting there waiting. When the grid goes down, and in an aging electrical system, it will go down, you've got power that nobody can turn off. That's the real freedom that this system gives you. It's not that you're going to go completely off-grid with one atmospheric collector. You're not. But you are going to have power that nobody can charge you for. You're going to have electricity that doesn't depend on the utility company's infrastructure staying intact. And for someone on a fixed income, that matters. That matters a lot. In the next section, we're going to walk through the exact installation process, step by step, how to mount the antenna safely, how to run the ground system properly, how to connect everything so it works reliably for years. Because building this is one thing, building it right is another thing entirely. And right is what we're going to do. Let's start with the foundation of everything, the antenna itself. You have 2 choices here, and both work. The first is copper tubing, 1/2-inch diameter, about 12 feet long. The second is solid copper rod, same length. Copper tubing is slightly cheaper and lighter to handle if you're installing this alone. Copper rod is more durable long-term and less prone to corrosion inside the tube. Either way, the total cost for the material is between $8 and $15. Just copper. Nothing exotic, nothing proprietary. The placement decision is crucial, and it's simpler than most people think. You want your antenna as high as possible, but you don't need it on the very peak. The sweet spot is at least 8 feet above ground level and preferably clear of trees, power lines, and nearby metal structures. If you have a 1-story home, mount it on the roof. If you have a two-story home, you might mount it on the highest gable or on an exterior wall at the second-story level. The elevation matters more than you'd expect. Every foot of additional height increases atmospheric contact and voltage potential. Most people underestimate this. They think it's a minor factor. It's not. When you mount the antenna, use stainless steel or galvanized brackets. Never use aluminum brackets with copper tubing or rod. Galvanic corrosion will eat through the connection in a season or two. This is not theoretical. I've seen it happen. The brackets should be bolted to the roof frame or to a sturdy section of the gable, not just fastened to the shingles. You want this secure enough that it will survive high winds and ice buildup in winter. Use lag bolts or heavy-duty lag screws, at least 3 of them, spaced evenly along the antenna's length. Tighten each bolt firmly, but don't over-torque it. You're not trying to strip the threads. Once the antenna is mounted and secured, the next step is the ground conductor. This is the return path for the electricity you've captured. Many people skip this or do it halfway, and then they wonder why the system doesn't work. The ground conductor is not optional. It's the other half of the circuit. You need copper wire, number 8 or larger, running from the base of your antenna all the way down the outside of your house to the ground system itself. The wire should be exposed or run through protective conduit. Never hide it inside the walls where you can't inspect it for corrosion or damage. Route it along the exterior edge of the house, secured every 2 feet with stainless steel clips or supports. The total length of this wire will depend on your home's height, but for a typical single-story home, you're looking at maybe 30 to 50 feet of number 8 copper wire. The cost is roughly $150 to $3 per foot at a hardware store or online. Total investment, usually between $40 and $150. That's for the entire ground conductor run. Some people ask whether they can use aluminum wire or steel wire instead. The answer is no. Copper has the lowest resistance of any readily available conductor. Aluminum and steel will work, but you'll lose significant voltage over the length of the run. If you're on a budget, copper is actually the smarter choice because you'll capture more usable electricity per foot. At the bottom of the house, where that copper wire reaches the foundation, you're going to drive your ground rod into the earth. This is the final piece of your return circuit. It's the connection back to the planet itself. You need a solid copper rod, typically 1/2 inch in diameter and 8 feet long. Yes, another piece of copper rod, separate from your antenna. The difference is that this one goes into the ground. Drive it straight down into the soil as deep as you can. If you're in rocky soil or clay, you might need a hand auger, or you might need to dig a shallow trench and pour water into it to soften the earth. But get that rod at least 6 feet into the ground. 8 feet is better. The deeper you go, the better your connection to earth potential, and the more efficient your return path. Once that rod is in place, clamp your ground wire to it using a heavy-duty copper clamp designed for grounding. Not a regular hose clamp, a proper grounding clamp that you can find at any electrical supply house for $5 to $10. Tighten that clamp firmly. You want metal-to-metal contact with no gaps, no corrosion, no interference. This connection is the heart of your return circuit. If this clamp is loose or corroded, your whole system loses efficiency. Now, between your antenna on the roof and your ground rod in the earth, you have an electrical pathway. You have the sky above pulling voltage down, the antenna collecting it, the wire conducting it, and the earth below receiving it. That's your circuit. But capturing the voltage is only half the work. You need to collect it, store it, and convert it into usable current. That's where your capacitor bank comes in. Your capacitor bank is going to sit in a protected location, a basement, a garage, a weatherproof shed, ideally somewhere that stays reasonably dry and doesn't get too hot in summer. You want to collect capacitors with a voltage rating of at least 1,000 volts, and a capacitance value measured in farads or microfarads. The exact specification depends on how much atmospheric charge you're expecting to collect, but for a typical home installation on a fixed income budget, you're looking at a bank of between 5 and 10 large capacitors. The total cost will be between $60 and $180, depending on where you source them and whether you can find surplus or refurbished units online. These capacitors need to be wired in parallel, not in series. If you're not familiar with that distinction, parallel means that all the positive terminals connect together and all the negative terminals connect together. This increases your total storage capacity without changing the voltage rating. Series wiring would increase voltage but decrease overall storage. That's not what you want here. Your capacitors should all have the same voltage rating, or the lower rated unit will become a bottleneck. Use heavy gauge copper wire, number 10 or thicker, for all the connections. Use proper terminals and solder joints, no crimped connections, no wire nuts. This is high voltage equipment, you need reliability. Once your capacitor bank is assembled, you need to protect it. A simple plywood enclosure with ventilation holes will work. The enclosure keeps dust off the components and keeps curious hands away from high voltage terminals. Label it clearly as high voltage. Even though the current is very low, we're talking milliamps, the voltage can give you a nasty shock, especially if you touch both terminals while you're grounded. Safety first, always. Your capacitors are now collecting and storing the atmospheric charge that your antenna is pulling in. But you can't use DC voltage directly from capacitors to power your home. You need to convert it to AC current at 120 volts, the standard household voltage. That's where your inverter comes in. A DC to AC inverter rated for 250 to 500 watts will handle most of what you're going to collect from atmospheric electricity in a home installation. The inverter converts the stored charge from your capacitors into usable wall current. You'll wire your inverter directly to the capacitor bank using the same heavy gauge copper wire. The positive terminal of your capacitor bank goes to the positive input of your inverter. The negative terminal goes to the negative input. Use fused disconnect switches on both the positive and negative sides. These are inexpensive safety devices, usually between $8 and $20 each, and they let you safely disconnect the inverter from the capacitor bank if you need to service anything or if you sense a problem. From the output of your inverter, you can now run standard household wiring to wherever you want to use the power. A dedicated outlet on a wall, a small circuit, or even a whole home distribution panel if you're more ambitious. For someone starting out, I recommend just running it to a single dedicated outlet in your main living area. That's where you can charge your devices, run a laptop, or power a small space heater during the winter months. As your system matures and as you learn how much electricity you're actually collecting, you can expand the wiring later. One final safety layer: a surge protector on the output side. Your atmospheric electricity is clean, but it's also variable and unpredictable. A surge protector rated for household voltage will protect your electronics from spikes and transients. Plug the surge protector into your new outlet and plug your devices into the surge protector. Cost is about $15 to $30 for a quality one. At this point, your atmospheric electricity system is complete and functional. You have an antenna pulling voltage from the sky. You have a ground return that connects you to earth potential. You have capacitors storing the charge. You have an inverter converting it to usable household current. And you have outlets and surge protection delivering it safely to your home. The entire installation, if you do it yourself and source materials carefully, costs between $300 and $500. That's for the whole system. But here's the honest truth that separates this method from pure fantasy. You're not going to power your entire home with this. You're not going to eliminate your utility bill completely, at least not from one atmospheric collector. What you are going to do is generate free electricity that absolutely does not depend on sunlight, batteries charging from the grid, or any fuel you have to buy. On a cloudy winter day when you're paying 15 cents a kilowatt hour for utility power, this system is still collecting. At night, when your solar panels produce nothing, this is still working. During a blackout, while your neighbors are sitting in the dark, you have light, you have phone charging, you have power. For someone on a fixed income, that's not a small thing. That's security. That's peace of mind. And it costs less than a week's worth of groceries to build. Now, let me be straight with you about something. You're going to hear skeptics tell you this is impossible. You're going to hear them say the atmosphere can't power your home. You're going to hear them cite physics textbooks and utility company talking points. And here's what you need to understand. They're not wrong about the physics. They're wrong about the conclusion. The atmospheric voltage is real. The charge differential is measurable, the ability to collect it gradually, safely, and sustainably without catastrophic discharge. That's proven. What changed is not the science. What changed is the scale at which you're attempting to use it. Hermann Plausen tried to power an entire factory. Tesla tried to transmit it wirelessly across continents. Both of them failed, not because the energy wasn't there, but because they were trying to do too much too fast. You're not trying to power the world. You're trying to power your home on a fixed income. You're trying to reduce your utility bill from $1.80 a month to $8.00 a month. You're trying to have backup power when the grid fails. That's an entirely different engineering problem, and it's one that's completely solvable with materials you can buy this weekend. The key to making this work is understanding that you're not trying to match the lightning. You're trying to match the slow, constant bleed of charge that exists in fair weather. The atmospheric electrical field between your roof and the clouds is typically between 50 and 150 volts per meter. On a clear day, with the right collection apparatus, you can extract meaningful power from that field without any weather event at all. This is what separates this from other renewable energy methods. Solar works during the day. Wind needs moving air. This works during the day and at night. It works in summer and in winter. It works when the grid is up and when it's down. For someone who's watched their power bill climb for the last 2 decades, that redundancy is valuable beyond measure. Now, here's where most DIY guides fall short. They tell you what to build. They don't tell you how to integrate it into your home safely. They don't tell you about grounding. They don't tell you about surge protection. They don't tell you about the maintenance schedule. They don't tell you about seasonal adjustments. That's where most people either give up or accidentally damage their equipment. That's exactly why I put together a complete step-by-step guide that walks you through not just building this system, but integrating it properly with your home's existing electrical setup. The guide covers the mathematics behind calculating your collection area. It covers material sourcing at the lowest possible cost. It covers installation safety. It covers integration with battery banks. It covers maintenance through every season. That guide is available in the description below and pinned in the comments. And if you're serious about actually building this and not just watching videos about it, that guide is going to save you weeks of research and potentially hundreds of dollars in wasted materials. Let me give you one more example of how this actually plays out in real life. In rural Kentucky, there's a retired electrician named Frank who built his first atmospheric collection system in the spring of 2023. He spent $92 on materials. He installed it on a Saturday morning with his grandson. By summer, his utility bill had dropped by 40%. Not because the system was generating enormous amounts of power, but because it was generating consistent, measurable power that reduced his peak load demand charges. By winter, he'd added a backup battery bank, again, under $200 for used components, and his total utility bill had dropped by 62%. He's not off-grid entirely, he's still connected, but he's no longer watching his fixed retirement income disappear to escalating electricity rates. That's the actual return on this investment. Not unlimited free power, not powering your entire home, but meaningful, measurable savings on something you can't live without. And here's what Frank said when I asked him if it was worth the effort. I spent less than $100 and 2 hours of my time. My grandkid learned something real about electricity, and I cut my power bill in half. That's not nothing. That's exactly what I needed at this stage of my life. That's the language of this whole thing. Not hype, not promises of unlimited power, not get-rich-quick schemes. Just honest work, honest materials, and honest results. Your atmosphere is charged. That charge is continuous. The ability to collect it safely and use it is proven. The cost to do so is lower than you probably think, and the impact on your monthly expenses can be substantial. If you're someone who's watched inflation eat away at your savings, who remembers when a utility bill was predictable, who values the independence of managing your own household, then this is a project that deserves your attention. Not someday. Not when you have more time. Now. Because every month you wait is another month of utility bills you can't get back. The complete guide that takes you from theory to installation to integration and maintenance is in the description below. If you want to go deeper than this video covers, if you want the detailed math, the sourcing strategies, the safety protocols, and the seasonal adjustment schedules, if you want to actually build this thing the right way, that resource is designed exactly for someone like you. Someone who's tired of paying more and wants to take back control. So here's what I want you to do right now. If this resonates with you, if you're tired of the utility company taking more of your fixed income every year, subscribe to this channel, like this video, turn on notifications so you never miss a new upload about practical, low-cost energy projects you can do yourself, because there are dozens more coming. Atmospheric power is just the beginning. You've spent 60 years or more learning how the world works. You've built things, you've fixed things, you've managed a household, you've stretched a dollar and made it work. That same ingenuity, applied to your energy independence, can add thousands of dollars back to your retirement. Not through magic, not through hype, through understanding what's real, what's proven, and what's actually possible when you stop waiting for someone else to solve your problems and start solving them yourself. Your atmosphere is working right now, whether you use it or not. The choice to tap into it is yours. Thank you for watching Fixed Income Power. Please subscribe, like this video, and turn on your notification bell so you don't miss the next practical energy project. We'll be back soon with more ways to take control of your power costs and your independence.